Hey there, science fans! Welcome back to another exciting episode where we unravel the mysteries of technology. Today, we're diving into the fascinating world of computer networks, specifically how computers talk to each other using something called datagrams. It's a bit like a digital conversation happening at lightning speed. Imagine you want to send a message to a friend across the country. You could write a heartfelt letter, carefully choosing your words. Then you send it through the postal service, trusting it will reach your friend intact. This is similar to how computers used to communicate using a method called circuit switching, where a dedicated path was established for the entire conversation. But there's a cooler, more efficient way: datagrams. Think of datagrams like postcards. Each one is a small, self-contained piece of your message. Each postcard carries a piece of your message along with the address of your friend and your own address as the sender. It's like sending little bits of information independently. You can send multiple postcards to deliver the entire message, ensuring that even if one gets lost, the rest can still make it. Now, unlike a letter that follows a predetermined route, each postcard travels independently through the postal system, finding its own way. They might take different paths and arrive at different times, maybe even out of order, but eventually they all get there. This is how datagrams work in computer networks. Each piece of data or packet travels independently, finding the most efficient route. Each datagram, also known as a packet, travels independently and doesn't rely on a pre-established path. This flexibility makes the network more robust and efficient. This method, called datagram switching or packet switching, might seem chaotic, but trust me, it's a game changer in the world of computer networking. It allows for faster, more reliable communication, even if the path isn't always straightforward. Let's break down how these digital postcards, our trusty datagrams, actually travel across the network. Each datagram carries a chunk of data, kind of like a sentence or two from your message, but it also carries vital information, like the addresses of both the sender and receiver computers. Think of these addresses like your friend's street address and your return address. These addresses help the network routers, which are like the post offices of the internet, figure out where to send each packet. As each datagram enters the network, routers analyze the destination address. They then decide the most efficient path based on network traffic and congestion. It's like choosing the fastest route to deliver your postcard, avoiding traffic jams along the way. This independent travel has some interesting consequences, which we'll explore in the next section. Buckle up, because things are about to get bumpy. Remember how each datagram travels independently? Well, this freedom comes with a few challenges. Since packets can take different routes, they might arrive at their destination out of order. Imagine opening your mailbox to find postcards from the same friend arriving in a jumbled sequence. Sometimes packets can even get lost in transit due to network congestion or errors. It's like a postcard getting lost in the mail. It happens. And in some cases, a packet might arrive multiple times. This duplication can happen if a router accidentally sends a copy of the packet on multiple paths. Don't worry though, these challenges aren't showstoppers. The beauty of datagram-based networks lies in their ability to handle these hiccups gracefully. So, if datagrams can get lost, duplicated, or jumbled, why use them at all? It's a valid concern, especially when reliability is paramount. Great question. Datagram switching offers some significant advantages over the old-fashioned circuit switching method. First, it's faster. This speed is crucial in today's fast-paced digital world. Since packets don't need to follow a preset path, they can take advantage of the most efficient routes available at any given moment. This makes datagram networks incredibly nimble and adaptable. Second, it's more efficient. Efficiency is key when managing vast amounts of data. Circuit switching requires a dedicated connection for the entire duration of the communication, even if you're just sending a tiny bit of data. Datagram switching, on the other hand, allows multiple users to share the same network resources concurrently. Think of it like carpooling for data, much more efficient than everyone driving their own car. This shared approach maximizes resource utilization. This flexibility and efficiency are crucial for the internet as we know it, allowing millions of users to connect and share data simultaneously. The ability to handle such a massive volume of data is what keeps our digital world running smoothly. But how do we make sense of all these packets flying around? That's where layered network architecture comes in. This structured approach helps manage and organize the complex flow of data, ensuring everything reaches its destination correctly and efficiently. Section 5. Layered like a cake, organizing the network. Imagine building a giant, complex machine with thousands of parts. It would be a nightmare to manage without some kind of organization, right? The same goes for computer networks. That's where layered architecture comes in handy. Think of a layered architecture like a delicious cake. Each layer has its own specific ingredients and purpose, but together they create a cohesive and delicious treat. In networking, each layer performs specific functions, working together to ensure seamless communication between devices. One of the most widely known models for layered network architecture is the OSI model, which stands for Open Systems Interconnection. This model divides the network communication process into 7 distinct layers, each with its own set of responsibilities. Ready to dissect this layered cake? Let's dig in. Section 6. Unpacking the OSI model. 7 layers of communication. The OSI model is like the blueprint of network communication, providing a structured framework that standardizes the functions of a telecommunication or computing system. Let's explore each of its 7 layers, starting from the top, closest to the user, and working our way down to the bottom, closest to the physical hardware. Each layer has its own unique role and responsibilities in the communication process. Layer 7 Application. This is where you, the user, interact with the network. It provides network services directly to end users and applications. Think of applications like web browsers, email clients, and video chat software. These applications rely on the application layer to communicate over the network. They allow you to access network services and send and receive data, making it possible for you to browse the web, send emails, and have video calls. Layer 6 Presentation. This layer ensures that the data exchanged between applications is in a format both sides can understand. It acts as a translator between the network and the application. It handles tasks like data encryption, decryption, and compression. This means it can transform data into a secure format for transmission and then back into a readable format upon receipt. Layer 5 Session. This layer manages the connection between 2 communicating devices. It establishes, maintains, and terminates the connections as needed. It establishes, coordinates, and terminates the dialogue between applications. This ensures that the communication sessions are properly synchronized and managed. Layer 4 Transport. This layer ensures reliable and efficient data transfer between devices. It provides error recovery and flow control to ensure complete data transfer. It handles tasks like segmentation of data into packets, flow control, and error checking. This means it breaks down large data into smaller packets for easier transmission and reassembles them at the destination. Layer 3 Network. This layer is responsible for routing packets across the network. It determines the best path for data to travel from source to destination. It determines the best path for data to travel from source to destination using logical addresses, like IP addresses. This ensures that data reaches its intended destination efficiently. Layer 2, Data Link. This layer manages the physical transmission of data over a single network link. It provides the means to transfer data between network entities. It handles tasks like error detection and correction at the link level and provides access control to the physical medium. This ensures that data is transmitted accurately and securely. Layer 1 Physical. This layer defines the physical characteristics of the network, including cable types, connectors, and electrical signals. It is the foundation of the network. It's responsible for the actual transmission of raw bits over the network cable. This layer converts data into electrical, optical, or radio signals for transmission. Remember, data travels down through these layers at the sending device and back up through the layers at the receiving device. Each layer plays a crucial role in ensuring successful communication. It's like a carefully choreographed dance of data. Each step is essential to the overall performance, ensuring that data moves smoothly and accurately from one point to another. Section 7. Application, communicating with the world. Let's start our journey through the OSI model with the layer closest to us, the application layer. This is where we, as users, interact with the network. Think of your favorite apps and software, web browsers, email clients, video streaming services. They all operate at this layer. Imagine you're sending an email. The application layer is responsible for taking your message, the recipient's address, and any attachments, and preparing them for transmission over the network. It's like packaging your thoughts and ideas into a digital envelope ready to be sent. This layer doesn't concern itself with the nitty-gritty of how the data will be transmitted. It's more about what kind of communication is happening, browsing the web, sending an email, or video chatting with a friend. It's the friendly face of the network, allowing us to access the vast world of information and services. Section 8. Presentation. Making data look good. Once the application layer has prepared the data, it's passed down to the presentation layer. This layer acts like a translator and stylist, ensuring that the data is presentable and understandable for the receiving application. Think of it this way: you wouldn't send a formal letter written in slang to a potential employer, right? Similarly, different applications might have different data formats and structures. The presentation layer smooths out these differences. One of its crucial roles is data encryption and decryption. It ensures that sensitive information, like passwords and credit card details, remains secure during transmission. Additionally, it handles data compression, making files smaller for faster transfer. Essentially, the presentation layer ensures that the data is dressed appropriately for the occasion, ready to be understood by the receiving application.